Okay, so are you ready for this? We're diving into the world of bioplastics.
Oh, yeah.
But not just any bioplastics.
Right.
We're talking about a starch-based plastic that's strong,
Huh.
flexible,
Interesting.
and get this,
Yeah.
self-healing.
Wow.
Right.
Okay. I'm intrigued.
This research is really pointing to a future where bioplastics could actually replace the petroleum-based plastics we use today.
I mean, that would be incredible.
It really would.
Yeah.
So the paper we're looking at today
Okay.
is from the South China University of Technology,
Okay.
and it's called Flexible, Thermal Processable, Self-Healing, and Fully Bio-Based Starch Plastics by Constructing Dynamic Imine Network.
Catchy title.
I know, right?
Yeah.
And it was published in the journal Green Energy and Environment.
Interesting.
And to help us break this all down,
Yeah.
we have our resident expert on sustainable materials.
Happy to be here.
I'm really excited to unpack this one.
Me too.
So before we get into the really complex stuff, I think it's important to remind ourselves why this research is so important.
Yeah, definitely.
We all know about the problems with traditional plastics, right?
Absolutely.
I mean, they rely on fossil fuels.
Right.
They persist in the environment for like ever.
Yeah.
And then recycling is such a challenge.
Yeah, it is. And all of those are huge problems that we really need to address.
Exactly.
Yeah.
So the search for alternatives, especially ones that come from renewable resources, is just becoming more and more critical.
Couldn't agree more.
So that brings us to starch.
Okay.
I mean, it's abundant.
Right.
It's renewable.
Uh-huh.
It's already used in some bioplastics.
Yeah.
But I have to admit, when I was reading this paper,
Yeah.
it kind of struck me that starch-based plastics haven't really taken off yet.
You're right, they haven't.
So what's the catch?
Well, starch, it does have a lot going for it,
It does.
but it also has its quirks.
Okay.
You know, it's kind of like
Mm.
trying to build a house out of wet crackers.
What?
They're brittle. They absorb water really easily.
Oh, yeah, that's true.
And trying to melt them and mold them is pretty much a nightmare.
Yeah, I can imagine.
So not really ideal if you're trying to make something durable and, something that's going to last.
Yeah, definitely not.
Yeah.
So how do these researchers overcome those challenges?
Okay, so this is where it gets really interesting.
I'm ready.
They use something called covalent adaptable networks.
Covalent adaptable networks.
Or CANs for short.
CANs. Okay.
Yeah.
That sounds a little intimidating.
I know it sounds complicated,
Right.
but the concept is actually really elegant.
Okay.
So imagine a polymer.
Okay, like the long chains that make up plastic?
Exactly.
Okay.
But imagine those chains have special bonds that can break and reform under certain conditions.
Okay, so the plastic can actually change its structure.
Yes, exactly. It's like giving the plastic a superpower.
It can adapt.
Yeah, it can adapt.
So instead of being stuck in one rigid form,
Yeah.
this plastic can actually change.
Yeah.
And that's what gives it its flexibility, its ability to be molded,
Yes.
processed with heat.
Right.
And this is the really wild part.
Yeah.
Self-healing properties.
Wow, no, right? It's pretty
Wait,
amazing.
so hold on, self-healing plastic.
Yeah.
How is that even possible?
It all comes down to the chemistry.
Uh,
They used a specific type of reaction called a Schiff-base reaction
okay.
to create these special bonds within the starch.
Uh-huh.
And they called them dynamic imine bonds.
Dynamic imine bond.
Yeah. And those bonds are the key to the material's adaptable nature.
So these bonds are like breaking and reforming all the time.
Yeah, pretty much.
And that allows the plastic to like rearrange itself.
Yes, exactly.
Wow.
That's incredible.
And it gets even more interesting.
Oh, there's more.
Oh, yeah.
Okay.
To create those dynamic bonds,
Uh-huh.
they used an ingredient called primine 10-1074.
Primine 1074.
Uh-huh. And that ingredient is derived from plant oils,
Plant oils.
like soybean and sunflower.
So that means this plastic is fully bio-based.
Oh, wow.
Unlike a lot of so-called bioplastics out there that still use petroleum-derived components.
Okay, so we've got adaptable self-healing plastic made from starch and plant oils.
Yeah.
I'm starting to see why you're excited about this.
It's pretty cool.
But I am curious,
Yeah.
when they actually created this material in the lab,
Yeah.
what did they observe?
Well, they included some really cool visuals in the paper.
Oh, yeah.
Yeah.
Like what?
SCM images?
SEM images.
Yeah, which allow you to see the material on like a microscopic level.
Okay.
And you can actually see the transformation from rough starch powder to this smooth, continuous film after they processed it with heat.
So it actually looks like plastic.
Yeah, it does.
That's pretty wild.
It is.
What about its strength and flexibility?
Okay, so they put the material through a bunch of tests,
Yeah.
and the results are pretty impressive.
Good.
It's surprisingly strong,
Okay.
and you can stretch it quite a bit before it breaks. Oh, wow. So it can hold up against traditional plastics.
Yeah, I mean, for example,
Mm-hmm.
they measured its tensile strength.
Tensile strength.
So that's how much pulling force it can withstand.
Okay.
And it was 5.4 MPa.
Okay. And how does that compare?
That's comparable to some conventional plastics.
Wow.
Yeah, it's pretty remarkable.
So it's not just biodegradable.
Yeah.
It's actually strong and flexible, too.
Exactly.
There's something else that caught my eye in the paper. They kept mentioning the low glass transition temperature.
Oh, yeah.
What does that even mean?
Okay, so the glass transition temperature,
Or TG.
or TG,
Okay.
is basically the temperature at which a material goes from a hard, glassy state to a more rubbery, flexible state.
Okay.
So think of it like
Yeah.
the difference between trying to mold a hard candy versus a soft piece of toffee.
Okay, so the lower the TG,
Yeah,
the easier it is to melt and mold the plastic.
exactly.
Okay.
And this bioplastic,
Yeah.
it has a TG of only 20.15 degrees C.
Which is similar to polypropylene,
And
a
that's...
very common plastic used in tons of different applications.
Okay.
And that means that it can be easily melted and reshaped, which is really important for processing and recycling.
Okay, that makes sense.
Yeah.
I have to admit, I'm still a little stuck on this whole self-healing thing.
I get it.
It's like something out of a sci-fi movie.
You know, right?
Can you tell me more about those tests?
Okay.
How do they actually demonstrate the self-healing properties?
They made cuts in the plastic film
Uh-huh.
and then applied heat and pressure, and the cuts pretty much disappeared.
Seriously?
Yeah, it's remarkable.
It just like healed up.
Pretty much.
Wow.
And they even measured the recovery of its mechanical properties after the healing.
Wait, so how much did it actually heal?
Okay, so they saw a recovery of 87.5% in tensile strength,
Okay.
92.9% in elongation,
Wow.
and get this, 94.5% in Young's modulus.
That's incredible.
It is.
So it almost completely healed itself.
It pretty much did.
Okay, so we've got strong,
Yeah.
flexible self-healing.
Yep.
Is there anything this plastic can't do?
Well,
Didn't we say that starch absorbs water really easily?
he did.
Yeah.
And you're right, starch is known for that.
Yeah.
But remember they added that Priamine 1074?
Oh, right, the plant oil.
Exactly. And those oils are hydrophobic.
Which means...
They repel water.
Okay.
And that gives the bioplastic its impressive water resistance.
So they kind of engineered a way around starch's weaknesses while still using its strengths.
Yeah, they did.
That's really impressive.
It is.
But there's one more thing I want to make sure we talk about.
Okay.
We've talked about how strong and durable this bioplastic is.
Yeah.
But what about biodegradability?
That's a really good point.
Yeah, we don't want it to just sit in the landfill for centuries.
No, we don't.
So did the researchers address that?
They did.
Okay, good.
They demonstrated that this plastic could be broken down both in a mild acid solution,
like
vinegar, and even with the Primine 1074 itself.
Hold on, the same ingredient that makes it water resistant can also break it down.
Yes.
That's amazing.
It is.
That's like programmable biodegradability.
It's a great way to put it.
That's incredible.
It is.
So we've got strong, flexible, self-healing, water resistant, and biodegradable.
It's quite the list.
I'm already starting to imagine all the ways this could change our relationship with plastics.
Me too.
But I think we need to take a deeper dive into those potential applications and implications.
Oh, definitely. There's so much to talk about.
Yeah, there is.
Yeah.
Okay, so let's do it.
All right, let's dive in.
I've been thinking about all the things we use plastic for, like just everyday things.
Oh, yeah.
Imagine if we could replace all of that with this bioplastic.
It's pretty mind-boggling.
It really is.
When you think about all the applications, packaging electronics, furniture, even car parts and building materials.
Exactly.
It's everywhere.
I mean, a lot of the bioplastics right now are just single-use items or packaging.
Right.
But this material, it just feels different.
It does.
It's strong, it's flexible, and we can process it with heat.
Yeah.
It feels like it could be so much more than just packaging.
Absolutely.
This could be the future of so many products.
Yeah. Yeah, I think we could be looking at a future where bioplastics aren't just the eco-friendly alternative,
right,
but the superior choice
for
so many applications.
Imagine your phone case or your laptop or even the dashboard of your car.
Yeah.
And it's all made from a sustainable, biodegradable material.
It's a pretty amazing thought.
It is.
Yeah.
It almost makes you wonder if there's anything this material can't do.
Right.
But I do have one question.
Yeah, okay.
We talked earlier about how easily it can be melted and reshaped.
Yeah.
So could that make it ideal for 3D printing?
I think so.
Yeah.
Absolutely.
Really?
Yeah, the low glass transition temperature and
Huh?
the fact that it can be molded and remolded.
Degrading. I mean,
Yeah.
that makes it perfect for 3D printing.
So we could see a whole new wave of product design and manufacturing,
Yeah?
all thanks to this material.
Potentially.
I remember how we talked about them being able to break down the plastic with a mild acid solution.
Uh-huh.
It got me thinking about composting.
Oh, yeah.
Could we actually compost our plastic products at home?
I mean, it's an incredible thought, isn't it?
It is.
I'd be able to just throw your plastic in the compost bin with your food scraps.
Yeah.
It would revolutionize waste management.
Yeah.
And it would really help us move toward a more circular economy.
And speaking of a circular economy,
Yeah.
this bioplastic can be melted and remolded multiple times.
Right.
So it can be recycled way more efficiently than traditional plastic.
Oh, absolutely.
I mean, we could create a closed-loop system where it's just recycled over and over and over again
Yeah.
without losing its quality.
That's the dream.
It really is.
Yeah.
And we can't forget about the Priamine 1074.
I mean, they showed they could break the plastic down using that ingredient.
Yeah, it's incredible.
I remember thinking, this is like programmable biodegradability.
Yeah, it's a remarkable concept.
What if you could design a plastic container with a predetermined lifespan?
Yeah.
So it would break down naturally after a certain amount of time.
Like sync to the expiration date of the food inside.
Exactly.
That would be amazing.
It would.
Yeah.
This level of control and precision,
Yeah.
we just can't do that with traditional plastics.
Nope.
Okay, so this all sounds amazing,
It does.
but are there any downsides?
Well, I think it's important to be realistic about the challenges.
Yeah.
As with any new technology,
Right.
there are going to be hurdles to overcome before we see this everywhere.
Like what?
Well, one of the biggest ones is going to be scaling up production.
Okay.
Right now, this research is just in the lab.
Right.
So we have to figure out how to produce this bioplastic efficiently
Yeah.
and cost-effectively on a large scale.
To make it commercially viable.
Exactly.
So it's one thing to make it in a lab,
Yeah,
but it's another thing entirely to mass produce it.
it is.
And what about the cost?
Yeah, that's a big factor.
I imagine producing this would be more expensive than just using petroleum-based plastics.
You're right. Petroleum-based plastics are often cheaper because the infrastructure for their production is already there.
Right.
But I think as the demand for sustainable alternatives grows and as production methods improve,
Yeah.
we should see that cost gap narrow.
Okay, so it's all about supply and demand.
Pretty much.
But there's something else I want to ask about.
Yeah,
We keep talking about how great this bioplastic is,
we do.
but what about its environmental impact?
That's a really important question.
Yeah, we want to make sure that producing it doesn't create new problems.
Exactly. We have to look at the entire life cycle,
Right.
from sourcing the raw materials to manufacturing, use, and end of life.
Yeah.
We need to make sure that the entire process is truly sustainable.
So what kind of unintended consequences could there be?
Well, for example,
Yeah.
we need to be careful about land use.
Okay.
We don't want to be expanding agriculture to grow the crops for starch and plant oils
Yeah.
and end up causing deforestation or displacing food crops.
Yeah, that would defeat the purpose.
Exactly.
So it's all about responsible sourcing.
It is.
Okay. So there's definitely a lot to consider.
There is.
But even with those challenges,
Yeah,
this research feels like a huge step forward.
it does.
I have a feeling there's a lot more to discover.
Oh, I think so.
I mean, we haven't even thought of all the possibilities yet.
I think this is just the beginning.
This could lead to a whole new way of thinking about materials.
Absolutely.
We're moving beyond traditional plastics
Yeah.
and entering a world where materials can be adaptable,
Uh-huh.
responsive,
Right.
and truly sustainable.
I think that's a great way to put it.
Okay, so I've been trying to think of other application for this bioplastic.
Yeah,
It's so versatile.
it is.
It feels like the possibilities are endless.
They really could be.
So what about the medical field?
Ooh, interesting.
Could this bioplastic be
Mhm.
used for things like implants or medical devices?
I mean, that's definitely an area that's ripe for exploration.
Yeah.
Yeah, you see, one of the things that makes this research so exciting is
Yeah.
that it's not just about the single plastic.
Right.
It's really about developing a platform technology.
A platform technology.
Yeah, a technology that can be adapted and tailored
Okay.
for all sorts of applications.
So they've basically given us like a toolbox.
Yeah, exactly.
Wow.
Like a blank canvas for material scientists and engineers.
So we could adjust the chemistry, add in different functional groups.
Yeah.
We could even combine it with other materials.
Right, and create a whole family of bioplastics.
Okay.
Each with its own unique properties.
So imagine bioplastics that are specifically engineered for different environments or tasks.
Exactly.
Like a bioplastic that can handle the crazy temperatures of space. Or a super flexible bioplastic for wearable electronics. Or maybe even one that can filter pollutants out of water.
I mean, the possibilities really are endless.
And really feels like we're blurring the lines between living organisms and synthetic materials.
It does, doesn't it?
It's wild.
Yeah, and that makes me think,
Yeah.
what if we could actually integrate biological components into this bioplastic?
Hold on. Are you talking about like living cells?
Yeah.
Like a living plastic?
Exactly.
Hold on.
Imagine a bioplastic that can sense and respond to its environment.
That's crazy.
Or one that can heal itself using biological processes.
That sounds like science fiction.
It does,
But you think it could actually happen?
I mean, the field of biomaterials is moving so fast.
It really is.
I wouldn't rule anything out.
Wow.
Yeah, it's a really exciting time to be in this field.
So this research isn't just about making a new plastic.
Right.
It's about opening up a whole new frontier
Yeah.
in material science.
It's about reimagining what's possible.
Exactly.
Challenging the very definition of what a material can be.
This has been an incredible deep dive.
It has.
My mind is blown.
I'm glad.
A huge thank you to everyone listening for joining us on this journey into the future of plastics.
Yeah, thanks for listening.
It's clear that this is just the beginning,
Oh, definitely.
and I can't wait to see what incredible innovations come next.
Me neither.
So keep asking questions, stay curious, and as always, keep diving deep.